I really am delighted to be here. And what I'd like to do is explain what a fab lab is. Many people would like a fab lab, but what is a fab lab? That's what I'll do. So I'm going to take about 45 minutes to first explain the research, then how fab labs appeared, and then talk about what they're growing into around the world and in Russia. So at MIT, I direct the Center for Bits and Atoms that works at the boundary of physical science and computer science. And one of the core themes from the research is there was a digital revolution in communication, there was a digital revolution in computation, but we're just at the edge of a digital revolution in fabrication. So these are among the most advanced manufacturing technologies today. But they're all based on this. In 1950, MIT connected the first computer to a milling machine. But I'm more interested in this. In this process, a child doesn't need a ruler to assemble Lego bricks. The parts measure position. The bricks are more accurate than the child, unlike the milling machine. And when you're done, you don't put the bricks in the trash, you disassemble them and reuse them. And so this is actually a more powerful process than this. Now, so what we're trying to do is not just have computers control tools, but actually put information into materials. And so we're progressing from computers running machines to machines that make machines, to putting codes in materials, to putting programs into materials. So to explain the background to Fab Labs, I'm going to tell a little bit about each of these steps. So in 1950, MIT connected a computer to a milling machine. Now what we're doing is making machines that make machines. So this is a machine that can make its own parts. And then for these machines, here's one that squirts, here's one that turns, here's one that extrudes, here's one that cuts. They use many different processes. And then for the machines, we've had to rewrite engineering software. So the software to design and control machines has to be rewritten for machines that make machines, and that's something that we've done a lot of work on. Okay, so the next step in is, instead of squirting or cutting, here's a machine that assembles parts like Lego bricks, but in this case it's for electronics, so you can make circuits by assembling and disassembling. This is an example of a digital material. The original design of this material was actually done by my daughter Grace, who's sitting in the front, and has led to these many different versions of these discrete digital materials. One of the versions of the digital materials we're using is with carbon fiber composites, and these are the world's lightest and strongest materials. And so we're using these to develop new ways, for example, to print an airplane. So those are examples of materials that contain codes, and then we're developing materials with programs. So this is a material where you have a code for a design, and the code actually turns into the shape of the design. The code becomes the design. And we've implemented that in proteins and microfluids and robots up in giant machines that can change shape. Now, that's not a new idea. That's how biology works. The idea is 4 billion years old. Codes becoming shape is how the proteins in your body are manufactured. We're now developing technology that works that way for things biology can't make. And so the ultimate goal, you might have seen in a Star Trek movie, is we want to make a replicator that makes anything by assembling the atoms. Now, to do that research, we bought all of these machines that let us make anything for the research. And then I had a problem. It took too long to teach people to use them. So I started a class in making things and was surprised by what the students made. This is a web browser for parrots. This is an alarm clock you wrestle with to show that you're awake. This is a dress with sensors that defends your space if somebody comes too close. And the way you can understand this is the killer application for digital computing is personal computing. In the same sense, with digital fabrication, you can do personal fabrication, which are not things you can buy in a store. It's things you can't buy in a store. It's inventions for one person. So mainframes went to mini computers, went to hobbyist computers, and then went to PCs. Now, the big machines, like in 1950, are like mainframes. The fab labs are like mini computers. The machines that make machines are like hobbyist computers. And the replicators we're trying to create are like personal computers. Now, here's the key point. The internet was invented in the period of mini computers. You didn't have to wait for the PC to invent the internet. So in the same sense, fab labs will get cheaper and faster and easier, but you don't need to wait 20 years to figure out how to use digital fabrication. And so here's then how fab labs started. So the US government asked us to do some outreach, and the fab labs were between. They were a small version of what we used at campus, but a big version of what the research will ultimately lead to. And then our plan was to only open one lab, but now there's about 100. And they spread because people don't just want information on a screen. They want to make things and measure things and change the world around them. And so as we spread them, the same sort of thing happening at MIT happened in these labs. And so the labs have been doubling about every 18 months. We don't run it, we help support it, but they've been spreading all around the world. Now, this is the location that's going to be renovated for the permanent site for the Fab Lab here, currently hosts Vladimir's laboratory. So now, to help you understand what's coming here, I'd like to show labs in many parts of the world and what they're doing. This is a lab at the University of Illinois in the Midwest in the US, and they used to have stations for farmers. Now what they do is they do outreach for technology. This is a lab in Maine, and they focus on artists, where artists come to the lab to make traditional crafts mixed with modern technology. This is a lab in Amsterdam, in the middle of the city, in the old customs house. And they made a project where they made a complete foosball table, including the scoring, and custom characters. So one team was me, and one team was Darth Vader. This is a lab in Manchester, and they're working on a new industrial revolution, where instead of shipping products, you ship data and produce the products locally when you need them. This is a lab in Barcelona of artists and architects and designers. Now, the team running that lab is now running the city of Barcelona. The mayor, the deputy mayor, the architect, all are linked to the Fab Lab. And so instead of buying products made far away, they want to make the city self-sufficient for technology, so that the city can produce the technology that it consumes. So that the skills and jobs are in the city rather than being sent far away. This is a lab in Detroit, and they focus on children in jail. They take kids who have either gone to jail or are at risk of going to jail, and they use the technology for social services. They take those kids and connect them back to society as the focus of the lab. This is a lab in Afghanistan that made a citywide internet in the lab so that data service comes from the community rather than from a big company. And in fact, all around the world, we're finding amazing kids. This is a girl from a township in South Africa. This is a boy in an Arctic village. And in the Fab Labs, they were doing the work of my classes at MIT. And so, for example, Hans Christian created this robot And Seymour Papert, who was the pioneer in computers in education, was very excited when Fab Labs appeared because he saw this as fulfilling his vision. He first let children program these machines, but what he really wanted was the children to be able to create the machine. And so he was very happy. He saw Fab Labs as fulfilling his vision. But we had a problem because now these students know more than their teachers, and the schools can no longer teach them. They're so far ahead of the schools. So we started a Fab Academy where we teach classes using the whole Fab Lab network. So it's a campus all around the world of students in these labs. So rather than having to leave town to go far away, they can stay in their town but connect with the world. This is a Fab Lab in Washington, D.C. At the end of the street is the Capitol building. And it led to this is President Obama visiting a Fab Lab. And it led to legislation looking at making a new national laboratory out of the Fab Labs. So you can think about the Fab Labs as a new kind of national lab made out of a network of local labs. And this was one of the most unusual ones. We set up a Fab Lab at the World Economic Forum in Davos in Switzerland in January for heads of state and CEOs to come make things. So as the community has grown, it's had meetings around the world. And there's now about 100 labs, and about every year and a half, the number doubles. Now I want to talk a little bit about what a Fab Lab is and what it isn't. So this is a Fab Lab in Africa, in Iceland, in South America, in the US. It's not like McDonald's, where they're a franchise and they all say McDonald's. Each has a local identity, but it's also part of a network. Now, all labs that fabricate aren't Fab Labs. We work closely with hacker spaces and maker fairs and many other aspects of this revolution. But the Fab Labs are unique in being linked in this global network and being based on this evolving technology roadmap. So there's an evolving inventory in all the labs that lets you make complete functional systems. And there's a set of rights and responsibilities that lets people and projects be shared in the network. Now, this has grown much too big for MIT. So from MIT, we're still very involved in the research, but we've helped create, beyond MIT, a foundation for operation, a fund for business, an academy for education. And so in many parts of the world, regional foundation programs have been set up. This is in the US and Spain, in the Netherlands and Japan, to help support the Fab Lab network. So a Fab Foundation is being created in Russia to help with the things that are hard for the local labs, like sourcing all of the materials, dealing with the vendors and customs, accounting, finding experts to help install, all of those things to help support the network. And then we're very happy to be working with MISiS as a technical partner to help have a reference lab with best practices and bring new capabilities into the network as it's developed. And we'll be collaborating with MISiS on developing the hardware, the software, the processes, the projects for digital fabrication. And so today there's education, there's research, there's business, there's incubation. Digital fabrication kind of turns all of that on the side. It means in a small space in a remote village, you can do all of those functions locally, but connect globally. The research project is the machines that make machines, so a Fab Lab can make a Fab Lab. But the bigger project that's emerged is how do you live, work, play, learn if anybody can make anything anywhere? This is a little bit like the birth of the internet. So together we're inventing new organizations for this new world. So that's what Fab Labs are. And so I thank you all for the work to bring it up to this point, and I look forward to working with you on their growth, and I'll be happy to take questions. Thank you.
Спасибо.